Okay, I guess we can get started. We're going to go ahead with our next session of the second day of our DeepMath conference. Just to remind everybody, if you want to ask a question, you can put it in the chat, the Q&A, or you can raise a hand. And in the last case, the tech chair will allow you to be able to speak. And we'll be trying to keep an eye on the Q&A to make sure that if there are any important clarifying questions that we can interrupt our speakers. So our next invited speaker is Raman Arora. He's an assistant professor of computer science at Johns Hopkins, where he's a member of the Mathematical Institute for Data Science, the Center for Language and Speech Processing, and the Institute for Data Intensive Engineering and Science. He's had stints of research at institutions like the Institute for Advanced Study, Simon's Institute for Theory of Computing at Berkeley, Toyota Technological Institute at Chicago, and Microsoft Research. And he studies a range of topics related to machine learning, stochastic optimization, and differential privacy. Has been especially productive in developing the foundation of deep learning. And today he'll be talking to us about, I assume, inductive biases and the algorithmic regularization in deep learning.
All right, thank you so much, Mikio, and thanks for the invitation to all organizers. So yeah, I want to focus on algorithmic regularization in deep learning. I want to highlight some broad set of ideas here, but let me begin with something that nobody here will dispute. I hope that deep learning is everywhere. It's transforming the world around us and is in many ways revolutionizing AI. It's also quite evident, hopefully, to all of us that deep learning here presents truly a generic learning system in the sense that we can use it to learn a whole host of different tasks, right? So if you feed it images and labels, outcomes, and or if we feed it, if we input it sample emails, it outputs a spam detector. If we feed it text and captions, outcomes a caption image captioning system. If we feed it, the text in parallel corpora, what we get is Google Translate, the translator, right? So and what is even more remarkable is that much of this advances really happened in the last 10 years or so. Back in the 90s, we nearly gave up on deep neural networks, given various computational hardness results, but also somewhat lackluster performance at the time, I would say, right? But this time around, things look quite different. The success we've already seen has been tremendous. The promise it holds is really incredible. And so a natural question to ask here is, what is different this time, right? Why do we have success now? Well, one explanation that's often put forth is that there is better compute now, faster compute now, and we have several orders of magnitude more data and the ability to store and process the data. But also to some extent, it's the effect of success begets success, right? The success of deep learning drove more people to it, and which drove even further success, right? But none of this truly really explains why we can solve problems that are known to be, NP hard in the worst case. Unless, of course, somehow we are hiding computation in this exponential growth in people trying to train such systems. But that sounds unlikely, although it would be honestly quite funny if that were to be the case. Another explanation that is often put forth is that deep learning works because it can learn hierarchy of features that can capture many natural phenomena, right? So for example, in image tasks, we can, this is another example that's even often this image that I often see is that we can learn these low level, mid level, and high level features by simply composing them on top of the other. And this, while interesting and somewhat compelling, is still a statement about what neural networks can represent, right? In fact, what neural networks can represent is something that we've known all along, right? I mean, this is a universal class in the sense that anything that I would ever want to compute, which is all the polytime computable functions, is representable by a neural network of size poly, right? So poly-size neural networks, which again have reasonable size, small size, bounded sample complexity, can represent all polytime functions, right? So this is an extremely rich class. It's learnable statistically, right? The problem though is that if I can learn this class efficiently, then I can learn all polytime computable functions, right? But that can't be the case, right? Or we wouldn't have crypto, for example, right? So this class must be hard to learn, right? And in fact, we've known that this class is hard to learn even if we look at extremely small size networks, right? Really tiny networks with just 3 neurons, right? And it's hard to learn even if we assume realizability by a neural network. So if the data is generated by a neural network, and even if we use a larger family of networks, right, or larger network to learn, right? So we look at over-parametrization or somehow combine multiple networks, right? So perhaps the right argument here is not what the reality is somehow captured by neural networks, right? The right argument here would be on the lines that since my data has certain magical statistical property, it is easier for me to train neural networks, optimize over neural network, right? So I argue here that what we would like to ask is not what reality can neural networks capture, but what is it about reality that actually makes optimizing over neural networks easier, right? And what is this? Well, we actually don't quite know. But what we do know is that this latest incarnation of neural networks as deep learning is quite rife with various algorithmic tricks and heuristics for training the network, right? In fact, I quite distinctly remember that when I first trained a neural network, still at TTIC, I was working on some multi-view learning of acoustic features for speech recognition, and everything worked out well if I followed a prescribed recipe, and it didn't work otherwise, right? And if it didn't follow the recipe, we really couldn't say why it didn't work, or if it would work or not, right? And many of these tricks were algorithmic heuristics that are still popular, such as weight decay, dropout, early stopping. There are also some that came more recently, for example, batch normalization, max out, and others perhaps that have fallen out of favor, right? For example, pre-training, which I always thought of as marinating a model overnight in unlabeled data, right? So the question here is to ask whether if this is what makes deep learning work, right? Many of these tips and tricks, if you would, follow from deep insights that researchers who've worked on these models for decades have about the task at hand, right? And this is what I would like to focus on this task in this talk, right? What we want to understand is what kinds of inductive biases do these algorithmic heuristics impart to deep learning, and under what assumptions on reality does it really make optimization easier? Okay. So here's the agenda for the talk. The focus on the first part of the talk will be on statistical aspects. Then we will quickly go over some computational runtime bounds, and we'll conclude with a brief discussion of the role of representation learning in all of this. I also want to admit upfront that we will focus primarily on matrix learning problems and learning two-layer ReLU networks. And what we're going to present is really far from a complete theory. This is intended instead to illustrate key ideas, and through analyzing a particular variant of algorithmic regularization, that of dropout. Right? So basically, we'll present a principled approach to analyzing algorithmic regularization, and we'll again illustrate these ideas through focus solely on dropout. Why dropout? Well, we'll see that it's first of all one of the most popular forms of explicit regularization. But also there's some very interesting connections we make here using Dropout, in a rather straightforward manner, which I don't see for some of the other algorithmic heuristics. Okay. All right, let's get started. So let me first remind you what is Dropout. So the key idea behind Dropout is that when training a network, we randomly subsample the network during the forward pass at each round. Okay? And we do so typically by drawing a Bernoulli random variable for each node in the network, independent of all the other nodes. And so for each node with probability P, we drop the node, or basically think of it as turning off the neuron, and with probability 1 minus P, we leave it on. When we drop a node, what it means is that there is no forward path through that node. We can think of setting the weights on all incoming edges and all outgoing weights from that node to 0. And I should say that the motivation for Dropout, as laid out in the original paper due to Srivastava, Hinton, Krishwatsky, Skeever, and Ruslan from 2014, was to ensure that each hidden neuron, each unit in the neural network, learns to basically work with a randomly chosen subset of other units. And this, as the authors argued, would drive each hidden node towards creating features which are useful on its own without relying on other hidden units, right, to correct its mistakes, right? So some kind of equity of contribution towards the final prediction, right? And they refer to this phenomena as breaking co-adaptation between neurons. Okay, so we begin by looking at Dropout in the simplest matrix learning task that we can come up with, that of matrix sensing. The problem setup is as follows. We're given n labeled examples. These are matrices xi and corresponding labels yi. The goal is to predict, given this sample, the goal is to predict labels for future unseen matrices drawn from the same distribution. And what we consider here is a realizable setting, right? So these labels are actually drawn according to some matrix W star, and these are linear measurements of some matrix W star using using matrices xi. Okay, so basically we can think of matrix sensing as recovering an unknown matrix given linear measurements of it. Okay, a natural learning rule here is empirical risk minimization, and in real world applications where we would use matrix sensing, we often have that the size of the matrix we are trying to recover is much larger than the number of measurements, right? So what we're going to assume here is that dt times d0 is much larger than n. And the only hope of doing so then is if we assume certain low rank structure on our matrix W star, right? And show that the sample complexity is somehow dependent on the rank of the matrix and not on the dimension of the matrix. Right? And a natural way to enforce such constraints, rank constraints, is to use a predictor W in a factored form UV transpose, where each U and V are some rank K matrices, right? That's the typical practice, right? What we're going to look at here instead is we're still going to represent our predictor W in factored form as UV transpose, but we're going to let these factors be, of much larger size than K, right? I mean, this D1, which is the number of columns in U and V, can be much larger than K. In fact, can be much larger than D2 and D0 as well, right? So we can think of this as an instance of overparameterization. Okay, so this is our learning rule. We basically simply look at empirical risk minimization. Given our data, we look for factors U and V, which are highly overparameterized, that minimize this empirical risk. Okay. And what we do here is we use Dropout to minimize these empirical risks. So what we do is that we in order to predict a label yi for a given input xi. What we use is a random subset of columns in the factors u and v. Right? And so we do this by modeling it using a diagonal matrix B, sandwiched between the factors u and v, where the jth diagonal entry of this matrix corresponds to a Bernoulli random variable. Okay, this basically determines whether the jth column of u and v participate in the prediction of yi given xi. Okay. All right. So with this description, what we can do is we can view dropout as an instance of stochastic gradient descent. Right. So we can think of SGD dropout as simply performing SGD on this empirical objective, where for each term in this finite sum that we have, we take expectation with respect to the random matrix. So we draw a random matrix, we estimate the loss, its gradient, and update using some gradient descent method to minimize empirical risk. We'll refer to this talk, this objective that dropout minimizes as dropout objective. Okay. And so the first question here is, how are these two objectives related, right? The one that I wanted to minimize and the one I'm ending up minimizing, given this is the algorithmic approach we took. Right? Okay, so we can show using some very basic calculus here that dropout objective can be written as sum of the empirical objective plus an additional term, which is data dependent, and we can view it as a regularizer due to dropout. Okay, and if you look at the form of this regularizer, again, this is a simple exercise to show this. What we can say here is that this is a cumulative sum of certain alignment between the hidden nodes and the ith training data summed over the sample. Okay. So the question that we want to understand here is that, given this is the form of the regularizer due to dropout, does it really provide any kind of capacity control? Does it yield any capacity control which can help with generalization? To show that, first we note here, the first thing we note here is that this regularizer actually concentrates around its expected value. And that's easy to show. So what we can do is then we focus simply on that expected value, and more importantly, it's not just the expected value which is of interest here. What we can also note here is that the loss here is as a function of W, the product of U and V. It's invariant to how we choose to represent our matrix W. It's really just a function of U times V. Whereas the data dependent regularizer here is, can be different for different parametrizations, if you will, of the predictor W. Right? So what we really need to look at to understand the regularizer that's induced by dropout is to look at the expected regularizer over all implementations, over all factorizations UV of a given predictor W. Okay, and this is what we'll refer to as induced regularizer. In general, this should be the quantity of interest, when we're trying to understand algorithmic regularization due to various different heuristics. Okay. So here is our first main result. What we show is that if we use Gaussian sensing matrices, so if our XIs, entries of XIs are IID standard normal, then the induced regularizer due to dropout is exactly equal to the nuclear norm scaled by the width of the network, or the size of the parametrization, which is D1. And this is actually quite amazing. Right? We said earlier that we could the only way we could give sample complexity bounds that are do not scale with dimension is by somehow leveraging the low rank structure in the predictor W star, right? That's the only way we could give dimension-independent sample complexity bounds, right? And what we find here with serendipity really is that the induced regularizer is indeed a nuclear norm which promotes low-rank solutions, right? So dropout here, in the context of matrix sensing under this distributional assumption is biased towards low rank solutions. Okay. I don't want to get into the proof details here, but I want to share an interesting finding here. So first, if we simply write out the regularizer for Gaussian sensing matrices, what we see is that it is equal to the product, to the sum over the hidden nodes of the product of the weights, of the incoming weights and the outgoing weights through that hidden node, right? And this is actually the same form as that of what people refer to as L2 path norm, which has been extensively studied and shown to provide size independent capacity control in deep learning. Right? So that's pretty cool. Another thing is that we can show, again, using a chain of very simple inequalities, that this expected regularizer is actually bounded from below by the norm, nuclear norm squared of the weight matrix W divided by D1, right? And it's easy to check that this lower bound is achieved if the factors are all equal and equal to the nuclear norm divided by D1, right? I mean, if I simply plug this value in the sum here, what I'll see is that I get the right hand side with equality, right? So I mean, this is easy to check that this is the setting of my weights which achieves the lower bound, right? And what this means again is that all factors, in some sense, contribute equally to the output, and therefore break co-adaptation between neurons, which was the original motivation for dropout. Okay. We also show, by the way, that this bound is not only achieved at for certain weight parameters. We actually show that this can be achieved using a polytime algorithm in the context of matrix sensing. So that's another interesting connection between what was the original motivation for dropout and formally instantiating in this language. Okay, so so another example is that of matrix completion. Matrix completion is simply an instance of matrix sensing where the sensing matrices are indicator matrices, right? So only one of the entries in the sensing matrix is 1 and the rest are 0. And we can sample this entry according to a joint distribution over the rows and columns of matrices, which are given by the product distribution over the rows and columns, right? So my indicator matrix Xi only has one of the entries, which is equal to 1, which is drawn according to distribution over rows P and distribution over rows over columns Q, right? And what we show here in this setting is that induced regularizer is proportional up to some scaling to the weighted nuclear norm of the matrix. So this should have been U and V. And think of U and V are the factors, which is the notation we were using. So sorry for the typo here. But the whole point here is that this induced regularizer is the weighted trace norm of the predictor, right? And this again is quite serendipitous, quite remarkable. The reason being that this is the right kind of inductive bias in various low rank matrix summation problems. The work prior, I mean, this work going back 10 years ago shows that we get optimal sample complexity bounds for a regularizer, which is the weighted trace norm, right? And we find here for dropout, again, something that we weren't looking for. Furthermore, what we can show here is that a generalization bound, which really follows from the prior work. All we do is bound the Rademacher complexity of predictors, which are bounded in this norm. And what we see here is that if I train through dropout a predictor whose regularizer value is smaller than alpha, then the generalization gap is smaller than something which is square root alpha d2 over n, right? So dropout directly controls this generalization gap. Okay, let's quickly go over some empirical results. I want to make one important point here. The main point here is to contrast the inductive bias we get using dropout and implicit bias we get using plain SGD. So this is on a movie lens data set. The details here are not important. What we are plotting here is, on the left is the training error, and on the right, the test error, the root mean square error for the task that we're solving. And what we see here is that vanilla SGD, so simply using SGD, it's best when it comes to minimizing the empirical error. It draws down the empirical error very, very quickly as a function of number of iterations. We also see that dropout controls the trade-off between approximation error and estimation error. As we increase the dropout rate, what we see is that dropout really favors solutions that are less complex, even though it comes at the expense of poor empirical performance. But when we look at the test RMSE, all of these predictors trained through dropout do fairly well. And in fact, the generalization gap actually decreases as we increase the dropout rate. What is most significant here, though, and this is what I want to emphasize, is that SGD, even though it's been shown to have certain implicit inductive bias, actually starts overfitting quite soon. And perhaps what we need here for SGD to work is some kind of early stopping, right? Which is yet another algorithmic heuristic, that we can think of as explicit regularization, right? So implicit inductive bias here, due to the choice of simply the optimization algorithm here, is not sufficient for this task. Okay, so here are some results that I'm going to skip in the interest of time. What I want to do is now switch over to neural networks, and we're going to look at the same setup with regression using square loss in the statistical setting. And so everything's the same here, except what we're using is a function class, which is represented by a two-layer ReLU network. Okay. The input dimensionality here again is D0, as we did for the previous case. The width of the network, or the size of the parametrization here, is again D1. And the output dimension here is, I'm going to denote as D2. Most of the time we'll think of D2 as just one dimension because we're looking at regression task. But we can also extend many of these results for multivariate regression. So I'm just gonna some places mention the more general result. If it gets confusing, you can always think of D2 as one. Okay. All right. And the only piece of notation that we need here is that the weights at the lower layer we're going to represent by this matrix P, and the weight vector at the top layer I'm going to represent with the vector U. Okay. Also, the activations coming into the jth hidden node, I'm going to write it as AJ of X. What would be of interest to us is really the outputs of the jth hidden node, which I'm going to represent as ZJ of X for a given input X. Okay. All right. So again, we train the neural network using dropout, which is again equivalent to minimizing the following empirical objective, where again we have this Bernoulli diagonal Bernoulli random matrix, which is applied to each of the outputs of each of the hidden activations of each of the hidden nodes, and using dropout, where during forward pass we randomly drop certain nodes, is equivalent to minimizing this dropout objective. Okay, so this is what we've seen before. So what does the dropout regularizer look like in this setting for two-layer neural network? So the expected regularizer here is again the sum over all hidden nodes. So sum over J, these index the hidden nodes, of the product of incoming weights and the L2 norm, L2 the second moment of the output of the corresponding nodes. Okay. So what does this tell us? What does this mean? What is the form of this? How can we interpret this this regularizer. So what we see here again is that, if we look at this quantity, and this is something that we want to control, this is something that we want to make small, right? We want to think of this as a regularizer. What should happen is that, if there's a lot of information that's passing through a certain node, right? So if Z of J, again, I'm thinking of this, the second moment as a measure of information passing through the node. So if there's a lot of information that's passing through a certain node, then the corresponding outgoing weight from that node should be small, right? So again, dropout here is promoting some kind of equity of contribution towards a final prediction, right? And it should not be surprising then that if I actually assume that the distribution over X was isotropic, then what I get again is that the regularizer here is simply sum over the hidden nodes of the incoming weights and outgoing weights, right? Again, what we see here is that the dropout regularizer in two-layer neural network manifests as L2 path norm. Okay, so the question is, what can we show in terms of capacity control for this regularizer? To answer this question, so this is again the form of the expected regularizer. To answer what kind of capacity control we can hope to get through dropout in two-layer neural network, what we're going to look at is the following hypothesis class, which is bounded in terms of some function of the data and the weights of the network. Okay, and this particular form of this function is motivated by the fact that we can easily bound this function in blue in terms of the regularizer that's induced by dropout, right? And this connection is important because we can check again here that this equality is tight if each of the terms in this sum is equal, right? So if each of the terms in the sum is equal, then this equality is going to be tight. And this is actually going to be quite loose if, for example, only some of the neurons are active at any time and responsible for the prediction, right? So if in fact dropout does break coadaptation, right? This is what we said in matrix sensing, it does, right? But if in the context of neural networks, if dropout does break coadaptation, what we're saying is that this inequality is tight, right? So what this means is that if I want to understand the class of functions, which are bounded in terms of the regularizer value induced due to the dropout, it suffices for me to look at this function class here. Okay. All right, so this is the function class we're going to look at. What can we say about this data-dependent hypothesis class? Well, in full generality, there's not much we can say, right? What we can show, in fact, is that there exists a distribution such that for even a single ReLU unit with bounded regularizer value, there is nothing we can say about a bound on the norm of this weight vector, right? So basically there exists distributions such that even for a network with a single ReLU unit, the network that dropout might return may not have the weight vector bounded in any suitable norm, right? And so we can't really hope to give capacity control bounds without any further assumptions, right? So to avoid this negative result, what we assume is something about a distribution. What we assume is something that is a bit weaker than symmetry. We assume that if we look at the half spaces associated with the decision boundary given by a single ReLU unit, the rectification unit, for any vector v, the half spaces in any orientation, what we assume is that each half space retains some beta fraction of the overall distribution mass, right? So basically what we're trying to say here is that if v transpose x is the input to a particular ReLU, then all of that information from the data is not squashed by passing it through through a ReLU unit, right? And again, the point here is to avoid a degenerate case where a ReLU unit quashes all of the input coming into coming through it. Right? We can argue that this will perhaps never be the case in any reasonable learning algorithm, but for simplicity here we just assume away such a possibility. Right? We refer to this property as beta retentiveness, where beta is the measure of distribution mass that is guaranteed to be retained when passed through a ReLU. Okay, so we think of beta as something constant. What we can show then is that for this class of functions under this beta retentiveness assumption on the distribution, the Rademacher complexity of the hypothesis class that we are effectively working with when using Dropout is bounded as alpha times a certain Mahalanobis norm of our sample with respect to the second inverse of pseudo inverse of the second moment matrix. So alpha times certain Mahalanobis norm divided by n. Okay, so this Rademacher complexity is bounded in terms of some data dependent property, which is shown here as a certain norm of this data matrix, times alpha. Alpha is the value of the regularizer of the network trained through Dropout, and n is the number of samples we have. Right? So basically the generalization gap here decays as 1 over n, where n is the number of samples. It also decreases if the Dropout returns predictors which have small regularizer value of alpha. And it depends on this crucial assumption that we made about our distribution, but for all practical purposes, I'm just going to think of this as a constant. And it also depends on certain data dependent property. If so if this norm is small, then the predictor that we return will generalize well. So the main takeaway here is that Dropout directly controls the capacity of this function class. We also show that the bound here is actually tight. I mean, this is the best we can hope for given such an assumption of beta retentiveness. One question that we pose as open in this work is whether this assumption that we make for beta retentiveness is necessary. It's quite possible that if we make a certain different assumption or additional distributional assumptions, we could get tighter control. But again, I want to emphasize here that this is something that's weaker than assuming symmetry. And in fact, if you can symmetrize your data by doing some kind of pre-processing, for example, then you can always assume that beta is simply equal to half. Okay. All right. A quick set of empirical results for neural networks. What we show here is that on the left is a generalization gap that we observe empirically on MNIST data set. And what we show here on the right is the theorized upper bound on the Rademacher complexity. We're hiding some of the other factors which just amount to scaling. What we're really looking at simply alpha over square root n. Okay, so on the left, again, it's the observed generalization gap. On the right is what we theorize as an upper bound on the generalization gap, right? And what's important here, really the main takeaway is that there is some correlation between the generalization gap that we observe in practice and what we can prove in terms of an upper bound. Okay, so before I move on to the next part of the talk where I focus on some computational aspects, I want to highlight something important regarding the role of parametrization in determining the inductive bias. Okay? So what we find is that if we do matrix sensing in the original domain, original space, so basically I don't choose to represent my matrix in terms of certain factors, but I actually do Dropout on the entries of the matrix W. Then for Gaussian sensing matrices, one of the cases that we looked at, the induced regularizer is equal to the rich penalty, L2 regularization. And it's quite bizarre, because I mean this is not really a suitable inductive bias for the low rank matrix learning problems that we consider. It doesn't really provide any kind of rank control, right? So representing our predictor in this factored model here really plays an important role. But that is not sufficient, right? That alone is not sufficient. What we also show is that if I simply look at a linear network and I represent it again in terms of factors, W1 through WK, and look at, again, regression, then the minimizers of the regularized ERM problem that will result from dropout simply amounts to solving this system of equations, which again is not doing anything for my predictor U. I mean, all it is doing is some kind of linear scaling of my predictor U. It's not controlling it in any reasonable or suitable norm, which would provide some kind of a rich inductive bias to the learning problem. Okay, so factorization alone is not sufficient. What we also need is perhaps some kind of ReLU nonlinearity that we had in two-layer radio networks. Okay, but then it's natural to ask what then explains the results that we just showed for matrix sensing, right? After all, matrix sensing, is there is no ReLU there, and we're looking at the predictor in this factored form as well, right? So actually, if I write down matrix sensing in factored form as regression using a linear network, what we require absolutely to be able to write this problem in that form is that that the linear network has some kind of a convolutional structure, right? So if we don't use a nonlinearity, we should at the very least have some convolutional structure in our factored representation. Okay? And again, this is pretty interesting. I mean, very simply looking at dropout in these matrix learning problems and simple two-layer ReLU networks, we can highlight, what role does parametrization play in determining the inductive bias, right? So again, without factorization, we don't get something that's rich. And without nonlinearity, I mean, factorization itself is not alone. Without nonlinearity, we again see nothing very rich. But a convolutional structure in the linear case will suffice. Okay. All right. So there's been a bunch of work, and I'm running out of time here, so I would rather just mention very briefly that much of the work that has preceded us has looked at dropout quite differently. One of the key distinctions between how we analyze dropout or look at dropout from what has happened before is that all of the works that precede assume certain norm bound already on the predictor, right? So they're using dropout, but they also assume that the weight vectors that they train are bounded in some norm, right? So what we look here specifically is no such assumption on the norm of the predictor, right? So all we're using is dropout. We're not assuming in addition that the norm of the predictor is bounded. And so all of the capacity control really follows from the dropout itself. Right? We do make some distributional assumptions, and that results in a certain data-dependent hypothesis class, which then justifies certain generalization guarantees. Okay? In terms of other related work, there's a bunch of work on analyzing other algorithmic heuristics such as weight decay, early stopping, and batch normalization. None of them, I think, highlight all the various interesting observations and connections we find here for dropout. But they're all very interesting results. Another line of exciting direction in terms of understanding the role of optimization algorithms more generally has focused on understanding the implicit inductive bias without any explicit regularization. And here the key insight is that the geometry of the local search plays an important role in determining the nature of inductive bias. This connection is quite well understood in convex optimization through online mirror descent framework, where the choice of Bregman divergence yields the desired geometry for local search. But this is much less clear in non-convex optimization, right? But I mean, it's not surprising that, you know, various choices of optimization algorithms, scale of initialization, learning rate, architecture, you know, somehow you know, affect the implicit regularization through the geometry of local search that they induce. I should note that there are certain challenges and deficiencies in all of this work. First being that for implicit bias, we already have results which show that, you know, even in stochastic convex settings, implicit bias may be insufficient to explain generalization in deep learning in overparameterized setting. And furthermore, there's also this issue of, you know, the existing works really plagued by really slow convergence rates. What I mean is that, you know, a lot of these works show that the empirical error goes to zero fairly quickly, but the rate at which the predictor approaches, you know, a max margin solution, or, you know, solution which is bounded, reasonably bounded in some norm that's induced by the optimization algorithm, it's fairly slow. It's very, very slow, actually. It decays as something as 1 over log p. Okay. Another issue deficiency which applies to the results that even we saw here is that, you know, possibly uniform convergence is, you know, unable to explain generalization phenomena broadly in deep learning, right? Even if we apply it to only to predictors that are returned by the learning algorithm, which was the case that we have here, right? So really, the only hope we have here is to rely on certain distributional assumptions rather than, you know, look at the worst case distributions and hope for certain data dependent bounds that are tight in practice and at least correlate well, you know, with practice. So this is what we tried here for Dropout, but, you know, of course, as I said before, this is not a complete story. What we as a community need to look for are magical properties of data that, you know, allow tight generalization bounds in the overparameterized setting, and something that, you know, also correlate with practice. Okay. All right. So I think, you know, I'm running low on time. Correct me if I'm wrong, but if that is the case, I might just skip over to the last part of the talk. I do want to say that, you know, in terms of computational aspects, what we look at here is, you know, again, for a two-layer ReLU network, we look at a classification problem, and, you know, where the goal is to find a network with small error rate. We look at the learning algorithm, which is simply empirical risk minimization using some surrogate loss, in particular logistic loss here. We look at dropout training, and we make a fundamental assumption, an important assumption here, which is basically that, you know, there is some separation between the class conditionals. So we're looking at binary classification problem. What we assume is there's some separation, there's some margin, you know, in the data, where when we use a predictor which is, you know, sufficiently overparameterized. So in particular, if I look at the RKHS of the NTK, the tangent kernel at initialization, then that RKHS has some predictor which achieves zero error with some margin. Okay, and this is really a key assumption here. So what we can show under this assumption is that if our predictor, if our neural network is sufficiently overparameterized, then even with constant learning rate, in t iterations, we find a predictor which has the expected error rate bounded by 1 over t. So after t iterations, I'm guaranteed that the expected error of, you know, the predictor returned by my dropout algorithm is going to be no larger than 1 over t, right? So we can find a good predictor that generalizes well in time that's polynomial in the problem size, right? And so relating this back to the, you know, looking at this result in the light of the question that I was posing earlier, the assumption that we need about reality here, which makes optimization easier, is that even when I look at very, very large networks, right? I mean, there is a predictor that's bounded from below, which does well on the task at hand, right? And it's important that's a necessary assumption. It's not just a sufficient assumption. It's necessary in the sense that my task is one that I can, solve well with a predictor that's quite large, right? And what I buy with that assumption is that, the training really becomes easier. Even if I initialize my network randomly, I only need to make very few updates to very small subset of parameters, and I can still very quickly converge to something that works very well in practice. Okay. All right. So I'm gonna skip these results. I do want to say that, another interesting, very cool result that we found with Dropout is that it really provides a kind of a generic regularization framework, right? In the sense that if I want to induce some other regularizer omega, I can simply choose to drop out hidden nodes with a certain data dependent parameter, and I'm guaranteed that whatever regularizer I want to induce will be given by will be induced by Dropout. Okay, let me stop here, and I intended to make some remarks about the role of representation learning, but let me just pause here and basically summarize what we just saw. So what we saw is that the algorithmic heuristics that are often employed in deep learning, they provide rich inductive bias that can help with generalization. And often these heuristics come from deep insights that practitioners have about the task that they've been working for a fairly long time, and it's useful to identify what these inductive biases are, to understand what is the role of the structure or network structure or the parametrization in determining these inductive biases. And in some cases, we can also build on these findings to create novel variants of the algorithms. Okay. Another takeaway, hopefully, from this talk is that what we really need here are certain data-dependent bounds that are tight in practice. They actually explain what we observe empirically. And to be able to do so, what we need is really the right set of assumptions that we need on a reality, right? So some certain generic distributional assumptions under which we're guaranteed to generalize well, and these bounds that we get in a data dependent manner are also capturing what's happening in reality. Finally, I think one of the fundamental questions that that all of this poses is really understand assumptions about reality that make optimization easier, rather than trying to understand what aspects of reality can the networks represent. I think the more pressing question is really under what assumptions about reality the optimization over neural networks becomes easier. Okay. All right, so I'll stop with that. Thank you for the attention, and maybe we have a few minutes for questions.
Yeah, we have a few minutes. If anyone would like to, yeah, go ahead.
Thank you for the talk. That was fantastic, and it was really interesting. I'm trying to piece together, the multiple types of implicit bias that rise up from these different tricks, right? So there's the implicit bias due to SGD, there's the implicit bias due to dropout, and right, you compound all these things. And so what I'm thinking about is, right, I'm digging deep here into some of the, I guess, middle old literature on matrix completion and whether or not kind of multiple regularizations help in the matrix completion problem. And I'm wondering if there's a sense that there's, different, right? This I think gets to your last point, different situations and different data sets where one of these regularizations that is implicit in one of these tricks is useful, but that, maybe none of the individual tricks are globally the right thing to do. Do you have a sense of like, is that the case, or, are some of these like better than others?
So I should say here that, what we're looking at is really just the, inductive bias due to dropout. I mean, I'm not sure whether, so we're basically saying dropout itself is an instance of SGD on this empirical objective, right? I mean, to me, if I'm doing dropout for, this finite sum minimization problem, whether I actually use gradient descent or not to minimize that empirical objective, that's not what I'm relying on here in terms of what geometry I use for local search. What I'm interested in understanding is, right, if I use dropout along with whatever way you had to minimize this problem, where at for each sample xi, I try to predict its label by using only a small subset of factors that represent my predictor, right? What is the basically inductive bias of doing something like that, right? So what we're really looking at is trying to tease apart what is the inductive bias for of dropout, right? So hopefully, we're not really mixing up, the inductive bias perhaps due to SGD with inductive bias due to dropout here. So I just want to clarify that first, right? So there may be some implicit bias of dropout itself, which could be that now, I don't really minimize this objective in expectation over these random variables. I actually sample from this distribution, right? So I mean, for every sample, I don't draw multiple dropout patterns, random subnetworks. I only draw a finite number of subnetworks for each data point, right? For each example. So there may be some implicit bias because of that, because I do it in a stochastic fashion even for dropout. And there's actually a paper by Shyam Kakade and Colin Wei, which tries to look at what is the implicit versus explicit bias of dropout. But the point I'm trying to make here is that it's what we are looking at is really the induced regularizer solely due to dropout. Okay, and to answer the second question that you asked, it is not clear. You're right. I mean, it is hard to tease apart if you're using a lot of different things. What effect do we have collectively? Using these algorithmic heuristics. It's a difficult problem. In fact, even for our setting, it's quite remarkable that we get some clean understanding of what role does a parametrization play in all of this. For some of the other heuristics that we have ourselves looked into, and there's been a bunch of papers, for example, early stopping, I don't think there's such a clean story here, right? I mean, this really drops out of trying to look at some of these results, which we obtain very simply, a little bit more carefully. And the role that network architecture plays here, fundamentally changes the kind of inductive bias dropout is imparting. Right? And so the point I'm trying to make here is that even trying to disentangle the effect that we get from choosing a certain architecture versus using a certain heuristics is often not that straightforward. At least in this case, we're trying to nail that down as well.
Great, thank you.
Do we have any other questions? I had a quick question. Maybe it's just I wasn't paying close enough attention, but back also to this matrix completion, matrix sensing setting. what I didn't catch in your results was that how the results depend on the overparameterization, namely this D1.
Right. Yeah, that's a good point. I didn't emphasize what role does D1 play here. I don't know if I have this on my slides, which would make things clear. But what we are hoping here is that let's see. Yeah, I mean, so one way to think about this is the following, right? So the induced regularizer is some scaling of the nuclear norm of the predictor with D1. Right? I mean, so if I increase the parameterization, I drive this to fairly small value. So actually, when I make my factors very large, right? I get a better handle on the generalization gap. And so this may not be evident from the bounds that I showed here, but this is what we observe.
So the implicit regularization is less important. I should say the implicit regularization of dropout is less important in the massively overparameterized setting.
It's I would say it's the other way around, right? I mean, so no, you're right. So it's the other way around, right? I mean, if I have over parameterized setting, so okay, so so I guess you're
I'm just looking at the 1 over D1 in this regularizer term here. Right, this would decrease. So higher D1 would mean lower weight on the regularization.
But this D1 may eventually figure into a bound on the radiometric complexity also. So I mean,
right. Okay.
Just looking at this, the nature of the regularizer here, it's not, I think, definitive in terms of whether the nature, the rank control aspect of the regularizer is diminished when we increase D1. Right?
Gotcha.
Okay. Although when we look at the computational aspects, I should note that again, what we said there was that the size of the parameterization actually plays a much more important role, right? So there, what we see is that as we make the network wider and wider, it becomes computationally easier to train the network. And the reason being that we, starting from any random initialization according to certain initialization scheme, what we need to do is really modify very small subset of, very small subset of our parameter vector, right? So in poly time operations, we can do that, right? I mean, and the larger the width is in those settings, I mean, the easier it becomes. But it comes at a very it comes at at the expense of assuming something very strong about reality, which is that the reality is realizable even with a predictor in the RKHS associated with the infinite width limit kernel at initialization, right? So essentially, it's nearly linear. I mean, so it comes at the expense of assuming something really harsh, not harsh, but strict about reality.
Good, Adam. You had another question. Okay. All right, then maybe this is a good time to move on to our next speaker. We can thank Raman once again. And Xingyu, if you'd like to go ahead and share your screen.
Sure. And let me share my screen now. Is it visible?
Yes, thank you very much. Okay, so our next contributed speaker is Xingyu Wang. He's a PhD student in industrial engineering and management sciences at Northwestern University. And today he's going to tell us how we can save ourselves from sharp local minima by truncating heavy-tailed noise in SGD.
Thanks, Mika. Thanks for having me. And it's my pleasure to share this joint work with Professor Sewon Oh and Professor Cheng Henry. So in this talk, we will discuss show that how with truncated heavy-tailed noise, we can almost eliminate sharp minima from SGD trajectory and improve the generalization performance when training deep neural nets. So we know that during the training phase, the input will be some training data set that are available to us, but in general, we are not sure how the model is going to generalize to the unseen test data. And in general, there is no guarantee on how large the gap or how small the gap is between the training and test performance. But to our surprise, methods such as SGD and its variants, even though they are very simple, they have been performing really well in terms of generalization performance when training large-scale deep neural nets. But the reason remains a mystery. Another mystery is if you think about if you cast the training task as an optimization problem, then on the non-convex landscape, there might be a plethora of local minima, but we are unsure why some local minima generalize better than the others. The reason here, there have been empirical evidence, there's a lot of empirical evidence suggesting that maybe geometric properties, such as being flat, makes some minima generalize better than the others. In particular, there have been a recent large-scale experiment showing that sharpness metrics seem to be the best ones when it comes to predicting the generalization performance. So given the SGD generalization mystery and this flat sharp minima folklore, there have been a lot of attempts trying to solve this question. Does SGD prefer flat minima? And if so, why is that the case? If we compare the deterministic GD iterates with learning rate eta to stochastic gradient descent, then the major difference is in SGD, you have gradient noise at each iteration. The typical assumption is these noises are light-tailed, but in this work, we'll focus on the heavy-tailed setting. By heavy-tailed, we mean that the noise distribution is regularly varying with index minus alpha. The meaning is just that the tail distribution, it resembles a power law, so it's polynomial with respect to x compared to the exponentially decaying tail with respect to x in the light-tailed case. So why do we want to focus on the heavy-tailed case? It's because there have been a stream of papers showing that first, reporting heavy-tailed gradient noises in deep learning tasks. Second, explaining why heavy-tails arise naturally in deep learning context. And more importantly, establishing that heavy-tail dynamics actually prefers flat minima. For instance, if you use heavy-tail dynamics to explore a landscape like this, then even though it's going to spend some time at all the local minima, it turns out that it will take longer for it to exit from such wider, flatter minima, thus providing a partial solution to the generalization mystery. But in this work, we're going to show that with minor modification to SGD, we can actually achieve a much stronger notion of complete elimination of these sharp minima from the SGD trajectory. So by minor modification, we are just referring to the standard gradient clipping. From now, we'll use B to denote the clippings ratio. That means at each iteration, you can move at most by distance B. So how does this help? Let's first look at some simulation results where we use different methods to explore this landscape. So under heavy-tailed SGD, if you do not clip it, you can see that it still spends some time around these two sharp minima. But once you start doing gradient clipping, then you can see that the time spent around sharp minima is almost completely eliminated. So this is what we are referring to when we mention the elimination effect. And also it seems like this is exclusive to heavy-tailed noises because under light-tailed noises in practice, it seems like it's very hard to escape even from a sharp minima. This may seem counterintuitive at first because if heavy-tailed noise facilitates exploration, then why would you want to truncate it and slow it down? To explain why this works, this is what we will do in the meaning of the talk. And to do so, we will revisit these two types of tail distributions. So for light tail distributions, the extreme values are very rare. For example, there's a photo of the tallest person known in the history of humankind. He's indeed very tall. But at the same time, we know that no one has been twice as tall as the average height of human being. In comparison, for habitat distributions, extreme values are way more frequent. For instance, the follower of an influencer on Instagram, it's going to be thousands or hundreds of thousands times that of an average user. The important thing here is if you compare a system under light-tail dynamics to a system under habitat dynamics, there is a structural difference in how rare events arise in these systems. More precisely, in light-tail system, you observe conspiracy principle. That is, if the system goes wrong, it's because everything goes wrong a little bit. Whereas in the habitat system, you observe the catastrophe principle. That is, when the system goes wrong, it is due to a few catastrophes caused by the habitat distributions. So we will see their precise meaning in our SGD context. Recall that eta is the learning rate. So when the learning rate is not too small in the SGD path, we can still observe the fluctuations, but as learning rate becomes smaller and smaller, it almost settles down on the gradient flow path, which is the ODE from the corresponding starting point. Also, the typical behavior will of course change if the initial condition varies, but more importantly, this will be the case regardless of the tail distribution of the noises. So if you look at this simulation result of the SGD path, here we are comparing light tail SGD with heavy tail SGD. At the beginning, when learning rate is not too small, it seems rather chaotic without clear pattern, but as learning rate becomes smaller and smaller, so we said that in both cases, the pattern is, the typical behavior is the same. They are just almost always following the gradient flow and being attracted back to the local minimum here. Now we know the typical behavior is the same, but what we'll be interested in is how the SGD actually exit the basin, so cross this barrier and leave the current basin to explore the other parts of the lost landscape. So that requires it to deviate significantly from its typical path, which means what we actually want to ask is how does the escape happens? How does SGD escapes local minimum? Recall that we mentioned catastrophic principle, and its precise meaning SGD is captured in the following result. For a rare event, so by rare event we mean that SGD path is very unlikely to fall into the set when learning rate is small. So for these rare events, there is a very important quantity that characterizes the dynamics. First, we know how rare the event is. This is roughly the order of the probability for these events. So recall that alpha is just a parameter dictated by the shape of the noise distribution, whereas this L star quantity, it determines how rare the event is. It determines the order of the probability. Moreover, if the real event actually happens, then the path, SGD path almost always just look like a piecewise gradient flow with, again, exactly L star jumps. That means most of the time, the SGD path just behaves normally following the gradient flow, whereas very occasionally there are some sudden catastrophes driving it away and trigger the real event. So what is this L star quantity here? It is the minimum number of jumps, catastrophes required to trigger this real event. So here we will see its precise meaning, again, in the question at hand, so the exiting of the basin. Technically speaking, there are infinitely many ways for the exit to happen, right? So as we are demonstrating here. But if you consider in the question, how many jumps do you actually need? Then of course you need at least one jump, and one jump will suffice to perturb the piecewise ODE outside, perturb ODE outside of the basin. So what the catastrophe principle tells us is SGD would almost always just look like these one jump paths when the exit actually happens. So this is indeed the case in the simulation result. Now we're simulating the path conditioning on it actually make an exit. So the path actually cross the barrier and leave the basin. So as learning rate becomes smaller and smaller, we can see there are two distinct patterns. In light tail SGD, if it exits, it's as if it's almost always continuously climbing towards the barrier and make an exit. Whereas for heavy tail SGD, it is behaving normally, following the gradient flow path until some sudden large jump, a single large jump, send it directly outside of the basin. And it only gets more interesting when you start adding gradient clipping. So recall that this is gradient clipping operator, and if the gradient clipping threshold B happens to be less than the radius, then one jump would not suffice because you can at most travel by distance B and it's not enough to cross a barrier. And under this clipping, you may need two jumps. What the catastrophe principle tells us is that these two jump passes, they will be the most likely way to exit for SG to exit under this gradient clipping scheme. Again, some simulation results this time under gradient clipping. So as learning rate becomes smaller and smaller, we can see that in the Lytle case, the pattern seems unaffected. This is exactly what we meant when we introduced conspiracy principle, because when the exit happens, so it deviates from the typical behavior. It is almost as if the path at any time point goes wrong a little bit. So it goes against the gradient flow. It is not being attracted back to the local minimum. Instead, it is moving toward the opposite direction all the time. Whereas in the heavy tail system, when heavy tail SGD makes an exit, most of the time it's still just following the gradient flow, being attracted back to the local minimum. But two sudden large jump trigger the exit and make the SGD escape from the basin. This is exactly what we meant by catastrophe principle. More importantly, the exact number of catastrophes is always as small as possible. Here are just some more examples showcasing that maybe you will need 3, 4, or even more jumps when the clipping threshold is even smaller, or maybe when the basin is even wider. Obviously, there's an important quantity, which is the L star, the integer part of the ratio between the radius of the basin and the clipping threshold, aka the number of jumps you need to make an escape. So clearly, this quantity will play a very significant role in the dynamics of heavy tail SGD. For instance, if we zoom in on a specific local minimum M and its attraction field, omega. So by attraction field, it just means starting from any point on this interval, the ODE path will be attracted back to the local minimum. We are interested in the first exit time, which is basically the number of steps you need to exit from the attraction field. And we have been using the term radius throughout. Its precise meaning is just the minimum distance you need to travel to escape. For instance, now the local minimum is closer to the left barrier, then this will be the radius. We have defined L star already as the minimum jump numbers. Note that for a fixed clipping threshold, the wider the basin is, the larger L star is. So it also tells you how wide the basin is relative to the clipping threshold. And we have proved the following result. So as learning rate goes to 0, the scaled first exit time just converges in distribution to exponential random variable. Here the scaling function, lambda, is just deterministic function and it behaves roughly polynomially. The point being, now we know that the order of the first exit time, it is roughly 1 over this lambda function, which means this is roughly sigma, the order of first exit time, it is roughly polynomial with this index. If you look at the index, L star is there, meaning that the wider the basin is, the larger L star is, the higher this order is, and the first exit time becomes significantly longer. So with this result, we can make sense of the elimination effect of sharp minima, because without gradient clipping, no matter how wide the basin is, you can always escape with just one jump, meaning that the exit time, the order of the exit time from any basin is gonna be the same. But if you start adding gradient clipping, then for sharp minima, if you can still escape with one jump, it doesn't have any effect on the order of the first exit time. Whereas for the wider basins, if now you need L star jumps to exit, maybe L star is 2, 3, 4, even larger, then the first exit time has a higher order. That means not only do you spend longer time here, but under small learning rate eta, compared to this term, all the other terms are almost negligible. So that's why we will have the elimination effect, because clipping doesn't really affect the first exit time at a sharp minima, but it makes you spend significantly longer time at the wider, flatter minima. So more precisely, what we said just means that for each basin, you should be able to define its own L star, the minimum jump number. For instance, if the clipping threshold is 0.5, then for these two basins, you can still escape with one jump. But for omega 2 here, you need to cross at least 0.6 to exit, which means you need to make at least 2 jumps. So this is how you determine the L star number. And in this sense, omega 2 is the widest one because it has the highest L star number. So this is how we define the widest minima here. And just by checking the L star number and see if it's the largest among all the candidates. We have the following result saying that, so on the left-hand side, it is a proportion of time that you spend. So outside of this widest basin, aka the proportion of time you spend at around narrow minima, it converges in distribution, in probability to 0 as eta goes to 0, as long as 0. So it means under small learning rate, as long as the training duration is not too short, then when you terminate the training, it is almost guaranteed that the address is not at the sharp minima. It also means that the proportion of time you spend, the SG trajectory spent in sharp minima is almost 0 when learning rate is small. So we have been focusing on our one case. Here we want to briefly mention that we have RD theoretical results, and we also have RD simulation results confirming the same elimination effect here. So we have these beautiful theorems, but do they translate well into benefits in actual deep learning tests? Here we propose a new training algorithm. By that we mean when updating the model weights, we're going to use the following iterates. So first, we will evaluate some heavy-tailed stochastic gradients and then clip it with standard gradient clipping. In particular, this so-called heavy-tailed gradients is just a standard small batch gradient plus some heavy-tail noise. So note that the distance between the small batch stochastic gradient and the full batch true gradient, it's a vanilla gradient noise. If you multiply it with some heavy-tailed random variable z, you get some heavy-tailed noise. Sometimes full batch gradient is too expensive and not entirely impossible to evaluate, so we use large batch instead. And depending on whether you use the same batch or the two independent batches here, you have two versions of the algorithm. So as we said, we have two versions of the algorithm, but in the result, you'll see that both of them outperform the others in terms of test accuracies. And also, if you evaluate this expected sharpness metric, you can see that the solution obtained by our method, they have a smaller sharpness value. And consider that there are so many different definitions for sharpness, so many different metrics. We have different experiments using different metrics, and the results, the pattern is consistent. In summary, our method finds solutions with flatter geometry and improved generalization performance. More importantly, if you compare it to this column, where we inject noises, heavy-tail noises, but without gradient clipping, the test accuracy actually deteriorated. So it seems like in practice, you do have to combine heavy-tail noise with truncations to actually see the benefits. Lastly, even in more sophisticated settings, when we start using techniques such as data augmentation or learning rate scheduling, the benefits of the truncated heavy-tail method still persists. So in conclusion, we have rigorously established an effect of eliminating all the sharp minima on the truncated heavy-tail noise. This is done by a sequence of delicate arguments about catastrophe principle, first X-time analysis, and metastability analysis in heavy-tail SG. Also, our tail inflation strategy manages to consistently find flatter solution with better generalization. And so that's the content of the talk. And please let me know if there's any question.
Thank you so much. That was a great talk. We have time for maybe one question.
There's questions in the chat.
Let me go check the chat. I haven't. I see a question about a figure. I think it was one of the first figures you showed.
Yeah.
The question is, in part C, why do you never find the position in, yeah. Yeah,
so yeah, thanks for the question. So in this case, we're using light tail noise instead. So we are making a comparison between heavy tail and light tail cases. So we are focusing on heavy tail, right? We said that it has the benefits of eliminating sharp minima. Here we're showcasing that it seems like this benefit is also exclusive to heavy tail noises in practice, because if you actually use light tail noises instead, then it seems like it's going to take astronomically long to even escape from a sharp minima. So that's actually the point of this figure, that is not escaping from the sharp minima.
Great. And so presumably then
the starting point is sharp minima. Yeah.
Yeah. Okay. Great. Any other questions? Okay, I think we will end this session here. Thank you again so much, Xingyu, and also if we can thank Raman again one more time, that would be great.